All right, we are ready. So I don't know what was going on with me last week. Remember that one that we were working on? And now when I sat down to do it today, I was like, well, yeah, it just works. So let's just go through and do that one, because I don't know what was going on. Let me grab the question here. We were working on the chain rule. Oh, like a beep, but I don't know where it was from. Anyways, so as kind of a quick review, we were working on the chain rule. And if you have something like f of g of x, then the derivative of this, right, d dx of f of g of x. So if you have a composite function, then the derivative is the derivative of the outside, so f prime at g of x, right? If we want to, I know we like the prime notation rather than the differential operators, but then we have to multiply by g prime of x. Oh, I see what's going on there. So, right, the derivative of the outside times the derivative of the inside, kind of implied in that, I don't know, mantra, I guess, is that you're evaluating the derivative of the outside at the inside, right? And then multiplying by the derivative of the outside. But once you have a handle on that chain rule, yeah, like I said, I don't know why I had such a hard time, but for assignment 3.4, question 11, we're given y equals 3 to the power of 4 to the power of 5 to the power of x. And then we were trying to decide how to go about doing this. And because we have the fact that, so then recall, I'll just put it here, the derivative d dx of b to the x is b to the x, b to the power of x. So it's, again, times the natural log of b. So here, x is going to be kind of the inside function. So then naturally, we're going to break this down and rewrite y equals 3. So that's going to be my b. And then everything else is going to be the inside function. So I'll need bigger brackets. I better write these out first. 4 to the power of 5 to the power of x is all in brackets. So here, 3 is my b. And this becomes my x, b to the power of x. So if we do y prime, well, so if we treat this as our b and this as our x, then of course it just becomes itself, and then it's the log of 3, right, because that's our b. But then we keep going, right, and then we've broken it down, so then we need to multiply by the derivative of the inside, right? So that's the derivative of the outside, and then we need to multiply by the derivative of the inside. So we get itself 3 to the power of 4 to the power of 5 to the power of x times the natural log of 3, right? This is basically the outside, how should I denote it? F prime at g of x. And then I need to multiply by, oh, I forgot. Happy St. Patrick's Day. I don't know if you can tell, but this is my greenest shirt that I have. And it's like a moss green. It's not very green at all. So then d dx, but I can use a green pen, how about?
I might be red-green colorblind, but even I can't mistake the shirt I'm wearing for green.
That's fair. Green's a tough color. I feel like no one really has green in there. When I first started teaching, I wore a green dress for St. Patrick's Day because I had like a green dress. And one of my students told me that I looked like an adult. I was like, oh, thank you. I guess. So then we want to take the derivative of the inside, which in this case is the 4 to the 5 to the x. So we've got the derivative of 4 to the 5 to the x. And then this is g prime of x, essentially, right? The inside. And then we keep going. So we end up with y prime is 3 to the 4 to the 5 to the x times the log of 3 times 4 to the 5 to the x, same idea, times the log of 4 times the derivative d dx of 5 to the x. Sorry, just a second. There we go. Okay, back. Okay, so then we just have 5 to the power of x. There's no more inside function. The inside function is x. So now we have y prime is 3 to the 4 to the 5 to the x times the log of 3 times 4 to the 5 to the x times the log of 4 times 5 to the x is just b to the x. So we have 5 to the x times the log of 5 times the derivative of x, technically, which is just 1, so we don't do that. There. Like I said, I don't know. I think I just needed a little bit of time to think about it. I have made quiz 6, I think it is. So quiz number 6 is this week. So this week we have quiz number 6, which it has 8 questions, which feels like a lot, but it's really just, find the derivative, and then find the derivative. So questions 1 through 6. 1 to 6 are on the chain rule. And just remember that you can combine the chain rule, or you might have to combine the chain rule with the product rule or the quotient rule, right? So just keep that in mind. The first one is a little bit weird, but when I did the quiz, it didn't take me very long, so I kept it in there. So, but if you're kind of like, oh, I don't know, it asks you to break down the function into the outside. So it asks you to give the outside function and the inside function. So just be prepared for that. But it's number 1 is a little different. Oops. But if you want to kind of have a booster right in the beginning, maybe go to question 2 and do a couple of those, get in the groove, and then you can go back to question 1. But I just want to give you a heads up that it's a little bit weird, but you should have definitely enough time. Was it 1 to? Oh, rats, 1 to 5, sorry. 1 to 5 is on the chain rule, and then 6 to 8 are using implicit differentiation, which is what we'll do today. So not as many, but they're a little bit longer. But once you get the idea of implicit differentiation, it's not that bad. But we have all the tools. but it's a little bit different. Okay, so I guess nothing to it but to do it. Here we go. I feel like there was another thing I wanted to say. It's not. That's not coming. So 3.5. Oh yeah, we've got our test. Test number 2 next week. Test number 2 next week. On Wednesday. It's just going to be up to whatever we get through, this week. So until the end of this week, I would love to have some time to do a review day, but we're kind of a little bit, not behind, but I'm feeling a little bit like we should get through some more material before the test. So I'm cutting the review day. We'll see if we have time. So I'm trying to do definitely 3.6, and then 3.9 I would argue is the hardest section of the course. So I'm putting that off until after the test. So we'll pick up 3.9 and finish chapter 3 after the test, but that should be good. So it'll be up to 3.6 and including 3.6. Right. So we'll do 3.5 today, which is implicit differentiation, and then 3.6 is logarithmic differentiation, which is pretty fun. And yeah. Implicit differentiation. Okay, so I'm just going to bring in the blurb from the handout. Now, do I have the handout? 3.5, yes I do. Okay. So I'm just going to grab this whole thing. No, I won't. I only want to talk about this chunk. So the difference between implicit differentiation and what we've been doing so far is that so far all our functions have been rearranged so that y equals something, right? So our output equals some function with respect to the input, right? So all our y's are on one side and all the x's or whatever the input is, theta, whatever, is on the right-hand side. So now we can still deal with expressions like x squared plus y squared equals 25. Now we could solve this for y, right? We could rearrange, but then, so this is of course a circle with radius 5, right? X squared plus y squared equals r squared. So a circle with radius 5. Thing with a circle, right? Because if we solve this for y, then we would have the positive and the negative version of the square root, right? So the negative would be the lower half of the circle and the positive would be the upper half of the circle. And so it just gets a little bit messy when we're trying to find the derivative. And then we have something even more extreme like this. X to the 3 plus y to the 3 is 6xy. If you tried to solve for y here, that's actually very difficult, right? Trying to solve for y explicitly. Hence, it's an implicit function, right? Because y is in there, but it's very hard. So very difficult to solve for y explicitly. So we leave it as an implicit function. So we leave it as an implicit function. And that's fine. That's why we need implicit differentiation. This function has a name, just like this is a circle. A lot of functions have names. And so this is called a Folium of Descartes. And there's a graph of it here. It's kind of a loop-de-loop. Well, let me mark this up so I can, oh, there, bump to the top. So here, this is what the Folium of Descartes looks like. Whee. Okay. So it's got this kind of loop-de-loop, and just like the circle has the negative, the bottom half, and the positive, now it's actually defined, kind of piecewise defined. Okay, so, but we don't need to worry about that because we don't need to solve for y, because we have implicit differentiation. So the key, right, even if we have something like this where we could solve for y, all the questions will say use implicit differentiation. So then, of course, we're just going to apply different implicit differentiation, right? And so even something here, right? What you'll find eventually is that it's just easier to use implicit differentiation than solving it for y and then differentiating. So, okay, the key to implicit differentiation is to recognize that y, so when I have y is a function of x, right? We don't know what that function is, but that means we need the chain rule, right? And so flashback to last day, I'll say, maybe in green, the key to implicit differentiation is to recognize that y is a function of x, is a function of x. Okay. So that means that y is some function of x, which means we need the chain rule around y. Okay. So this requires the chain rule. Because, and that's the hardest part with this implicit differentiation is that you only get y, right? Y squared. So for example, if you have something like y squared, right, and you're trying to find d dx of y squared, what you actually would end up having is that 2y, right, the derivative of the outside, technically to the power of 1, I'll just throw it on there. But then, oh, actually, I'm not going to put to the power of 1 because it looks like a prime, and I'm about to write a prime. Could be very confusing. And we don't need this power of 1. But then I need the derivative of the inside, but I don't know what that is, but it's okay because then we just use times y prime, right? And so here, this is the outside. And then here, this is the inside. Okay. And then if you're trying to find y prime, you can rearrange your equation to solve for y prime, right? So then we can rearrange. And I just did a quick silly example, so we'll see it better in a little bit here. But then we can rearrange to solve for y prime. And I'm just going to go straight for the prime notation. We should be using ddx or something like that, but it's just nice to have y prime. There's a lot going on with implicit differentiation anyways, so yeah. All right, so we'll just go for it. Let's just find the steps. Although they're pretty straightforward, we kind of did them here already, so we differentiate with respect to x. So here, this is the reason that there's no x explicitly here, right? And so the x must be inside the y. We don't see what it is, but we know how it would behave, right? Y prime. So, okay. So the steps that we're going to follow is you differentiate with respect to x, right? So if you have an x, you can just treat it like we've been doing regular derivatives, right? And so the first step is to differentiate both sides. Often you'll have something like the Folium of Descartes here, where you have a left-hand side and a right-hand side, right? Even here with the circle, x squared plus y squared equals 25, we have two sides. So we differentiate with respect to x. Way. We differentiate both sides of the equation with respect to x. Of the equation with respect to, usually I just write WRT, but I'll introduce it there with respect to x. Okay. Applying the chain rule, so just like we said, applying the chain rule to y equals f of x. Okay. And then our second step is, like we said, to solve for dy dx or y prime. I'll say solve for y prime or dy dx if you prefer that notation, but I know you don't. I feel like we've established that. You guys prefer the primes, and me too. All right. So let us do example 1. Copy. So it's the same old song and dance. We want to find an equation of the tangent at some point, which means, okay, well, the slope of the tangent line, how do I find it? Well, I have to take the derivative. That's still the slope of the tangent line, and I have a point, and here we're actually working with that circle with radius 5, and we're at some point 3, 4. Okay? So first we're going to find the derivative of this thing. So this is the first time that we're seeing implicit differentiation, and here we go. For real. So if we have x squared plus y squared equals 25, without the dy dx or kind of d dx notation, it's hard to illustrate that you're going to take the derivative, and it doesn't really make sense to kind of just jump in and do the derivative without telling anyone on paper that that's what you're doing, right? So for that reason, I'm going to wrap it up on the outside here. D dx of x squared plus y squared equals d dx of 25. Right? Later, I'll switch to prime notation, but this is just to illustrate that I'm going to be taking the derivative now. Okay? So here, I essentially have a polynomial, but just remember that the, oh yeah, hit me. Turn off my volume.
So you need to I assume that we need to, if we're deriving one side, we also need to derive the other.
Yes.
Okay.
Yeah.
So same as before. What happens to one side happens to the other. Good to know.
Good. Yeah, totally. And what's nice is especially if you have a constant over here, it goes to 0, right? And it kind of cleans it up a little bit. But yeah, so you want to take the derivative of both sides, especially because later, when we do this little guy, the x to the 3 plus y to the 3 equals 6xy, right? Then you definitely would have to take both sides. All right. Okay. It's so laggy today. Weird. I think I say that every day though. Wow. Okay. I think we're back in business. So here, to start off with, we basically have a polynomial. I know how to take the derivative of this thing, but then I also need to pump the brakes a little bit because I have this y that I need to deal with, like the chain rule. And then I have the derivative of a constant, which we know goes away. So here, when I take the derivative, well, the derivative of x squared we know is just 2x. And then when I take the derivative of y squared with respect to x, right, the derivative of the outside is 2y to the power of 1, but I'll just write 2y. And then we have to multiply by y prime. And then the derivative of the constant is 0. Right. So here, I'll just say you could write d dx of y or dy dx. They actually are the same thing. But I'll try to stick to prime notation usually. Right. So that was our first step with implicit differentiation, right? So differentiate both sides of the equation with respect to x. So the respect to x is the hang up. And we do that when it's yeah, exactly. Because the y is a function of x. We just can't see it. So then, and that's always going to be the case. We're always going to differentiate with respect to x when we're doing it implicitly. And then we have to manipulate the y there. Yeah. Good. Okay, so we've done the first step, right? And we applied the chain rule to y equals f of x. So now I want to rearrange and solve for y prime. So here we go. So now solve for y prime. So what I can do is I can say 2y times y prime equals negative 2x, right? Moving that 2x over to the right-hand side because I've got that 0, I can subtract 2x from both sides. And then trying to get y prime on its own, I get negative 2x over 2y, which of course is going to cancel. So now I have y prime is negative x over y. And that's the derivative. Great. This is the derivative. Whee. Great. Now, I think we had some more parts. Yeah, we want to find the equation of the tangent line. So this was part A. Okay. So we wanted to find dy dx. Dy dx is just y prime. So that's fine. And then we want to find an equation to the tangent line on the circle at the point 3, 4. And so now x is 3 and y is 4. which means we can substitute those in to find the slope of the tangent line. So part B, we want to find, I'll just summarize here, the equation of the tangent line at 3, 4. And I'm just going to emphasize here that this means that x is 3 and y is 4. And from that, I know that y prime is -3 over 4. And this is the slope of the tangent line at 3, 4. Because that's the definition of the derivative. So the slope of the tangent line at 3, 4. So now I have the slope. Once I have the slope point, I can use the point slope form of a line, and I can construct this and say that y minus y naught is m times x minus x naught. So y minus the point of y that we have is 4, and the slope is -3 times x minus 3. From here, I think we feel pretty comfortable moving stuff around and solving for y potentially, or sometimes if we started with an implicit function, sometimes we rearrange it to another implicit function for some reason. But so let's just rework this a little bit. So I get y equals -3 over 4x plus 9 over 4 minus, sorry, plus 4 because I added it to both sides. Okay, I'm going to need a common denominator here to combine these constants, 9 over 4 plus 4, which means I need to multiply 4 by 4 over 4. And I get y equals -3 over 4x plus 9 plus 16 over 4, putting me at plus 25 over 4. Now, because I have a common denominator here, I can put them all over 4. And I could rewrite -3x plus 25 over 4. I would say that this is plenty. In fact, I personally probably would have stopped here. That's fine, right? As soon as I have it in the form of y equals mx plus b, that's enough. But then, you know, we saw that we had this common denominator of 4, so why not smush it together? We can take it even further, right? We can rewrite further by multiplying the y by 4 if we want to, right? So then we have 4y equals -3x plus 25. And then if we wanted to make it match the original equation, right, I could add 3x to both sides. So then I have 4y plus 3x equals 25. Right. We can morph this thing all day, right? But here, I would say we're kind of back to an implicit function. It's easy to rearrange and solve for y, right? We would just, you got it. Is that enough?
Yeah.
So easy enough to rearrange and solve for y, but sometimes they like to get fancy and go back to an implicit function, but it's okay. So here, I'm just gonna write, now we're back to an implicit function. And I'm putting implicit in quotes because when there's just one y, I wouldn't really call it an implicit function, but implicit function, but it's easy to solve for y. In fact, we actually unsolved for y here, right when we took it further and further. Good. Okay. So let's do more examples. Right? So that's our kind of our first one, and it is weird, but of course, I don't know if you've done the implicit differentiation lab. I think the labs sometimes they move a little bit faster than I do because I'm a little bit slow. But of course, Maple does. It has the implicit diff command, and then it just does it for you, right? Which is nice, but we need to know how to do it for real. Okay, let's do example 2. Oh, did you get what you needed, Jaspreet?
Yeah.
Okay.
Thank you.
No. All right. Let's try this. Let's try tackling this Folium of Descartes. And oh, maybe I should put it on a fresh page. It's kind of a big one. Nice to start fresh. If you try it on your own that might be nice. Looks like David already is. That's why I'm. Okay. We'll go ahead and get started on if you're still working on it, that's great. We'll get started here. So if you have x to the 3 plus y to the 3 equals 6xy, one thing that I want you to kind of notice is that here you're going to have the product rule, right? And so it's kind of got that extra step of the product rule on the right-hand side. Maybe I'll do. It doesn't matter if you use 6x as a function or 6y as a function, right? But you'll want to put the 6 with one of these and treat that as your function. For me, it just is more natural to do 6x as one function and then y as another function, but whatever you want. So again, just to indicate that I'm about to take the derivative here, I'm going to wrap it up in ddx's, but then I'll switch to y primes because it's a little bit cleaner. So I'm going to have d dx of x to the 3 plus y to the 3 equals d dx of 6xy. Now, x to the 3, we know what we're doing there, right? And so that just becomes 3x squared. Same thing with the y to the 3, but now just remember that y is implicit. So you have this 3y squared. And then don't forget the times y prime. Right? The derivative of the outside times the derivative of the inside, which we don't know what it is, but that's okay. I'm going to make a note here that for my product rule, I'm going to use f is 6x and g is just my y, right? And just remember the product rule of f times g prime is f prime g plus f g prime. Right? Kind of a reminder from last week. Okay, f prime is the derivative of 6x, which is just going to be 6, right, times g, which is just y, plus f, which is just 6x, and then times g prime, which is just going to be y prime, because it's just y, right? The outside function is y to the power of 1, but when you do that, you don't need to worry about it. It just becomes y prime. So now I have a y prime here and I have a y prime here. So here we've differentiated with respect to x on both sides, and now I want to rearrange and solve this thing for y prime, right? No more derivatives have to be done, right? We just need to rearrange and solve for y prime. So I'll just make a note here. We're going to rearrange and solve for y prime. Okie dokie. So we have 3y squared times y prime. So I'm going to keep my y prime terms on the left-hand side, and then all my non-y prime terms I'm going to move to the right-hand side. So minus 6xy prime equals 6y minus 3x squared. Make sure I did everything legally. I did. Okay, good. So then now I can factor out a common y prime. So I get y prime times 3y squared minus 6x is 6y minus 3x squared. Home stretch here, solving for y prime, not bad. It's remembering that chain rule on the y, that's the hardest part, I think. So then solving for y prime, I can divide both sides by 3y squared minus 6x. So I get 6y minus 3x squared over 3y squared minus 6x. Depending on how simplified you want to get, you could factor out a common 3, but that's about it, right? You could leave it like it is too. I'm pretty sure that WebAssign would accept this just as it is. We can simplify a little bit further, and I'll just say this is kind of an optional simplification. Because we're going to be using the y prime later, I think it's going to be nice to have kind of a cleaner y prime. So then y prime is 3 times 2y minus x squared over 3 times y squared minus 2x. Having a hard time dividing by 3 today. So then these 3's I can cancel. So then I have y prime is 2y minus x squared over y squared minus 2x. Okay. So that was part A. If you just kind of look at this, most of the work is happening with just straight math, right? It's not actually the derivative, but you do want to take your time and spend it, right? The derivative was just kind of over and done with almost immediately, but you do want to keep wits about you that you're doing the chain rule on your y's, and then it's just a matter of rearranging and solving for y prime. I shouldn't say just. This stuff is hard when you're first doing it. So I think there were multiple parts here. So let me scroll up and see. Okay, so now we have the derivative y prime, which is the slope of the tangent line at some value of x and y, or some point. So once more, and I'm pretty sure for, I don't know how many years, definitely on the Maple lab exam. I don't know if you have to do a Maple lab exam this term, but this is basically the question that, or one of the questions that you have to do, or at least when I was teaching it, this is, yeah, pretty typical that they make you do a Maple lab exam. Some things don't change. And cool, yeah. So at least as many lab exams as I have seen use basically this exact same question, but in Maple, right? So so it uses the Folium of Descartes or something similar, and then you have to find the equation of the tangent line at some point, and potentially even some point where the tangent line is horizontal. So let's go ahead and do it. But then as we're doing it, the reason I mentioned that is because it might be nice to think about how you would go about and do it in Maple. And I'm sure there's an exercise in that Maple lab manual that does it as well. Okay, so B, we wanted to find the equation of the tangent line, at 3, 3. So first thing I'm going to do is I'm going to find the slope at 3, 3, which is of course y prime when x is 3 and y is 3. So I get 2 times 3 minus 3 squared over 3 squared minus 2 times 3. 6 minus 9 is -3, and then 9 minus 6 is 3. So I'm going to skip ahead because I've got a page break here. So y prime is -1, -3 over 3. Okay. Because we have the graph of this function, how about we have a look at and make sure that what we're saying makes sense. All right, because what we're saying is that, all right, at some point, let's say negative 3, 3, and maybe something tells me it's out here on the edge. Or sorry, 3, 3. It makes sense that the slope of the tangent line is -1, right? At least that it's negative, right? We can't really confirm the actual value of the slope, but -1 seems reasonable, right? So as soon as you have the graph, it's nice to just confirm what we found and make sure it makes sense. So then the equation of this tangent line that we just wrote, let's say is y minus y naught equals m times x minus x naught. X is 3, y is 3. And so y minus 3 is -1 times x minus 3. So I get y is -x plus 3 plus 3. Just so I don't have a negative x, I'm actually going to write this as 6 minus x. But that's just because it looks a little bit nicer. Nice. So this y equals 6 minus x would be the equation of this line here. Okay. You could even rearrange this implicitly, right, to kind of match the original function, right? So you could write y plus x equals 6 if you wanted to. You don't have to. Okay, good. So what's the next thing we have to do? I think we have to find where now let me see if it can keep up with my scroll. So now we want to know at what point, so we don't know what xy point in the first quadrant is the tangent line horizontal. So we need to remind ourselves what it means for the tangent line to be horizontal, right? It means we have a slope of 0. And so it means that the derivative has to equal 0 for this to be true. And maybe I'll copy this because I don't want to rewrite that. And I don't want to keep scrolling around for it. Whee. Okay, so I guess we could copy, could paste this again here. And now we're moving on. We're doing another one, but it's the same graph. So really what we're asking is, well, we have to stick to the first quadrant, right? So that's here. And maybe I'll do kind of like we're restricting our domain and our range to be in this little blurb here. And then it does look like at some point here, it looks like we might have a slope of 0 for the tangent line. So recall the tangent line is horizontal if it has a slope of 0. Therefore, right, remember y prime is the slope of the tangent line. And let's just remember that y prime is the slope of the tangent line. So y prime, which in our case we found was 2y minus x squared over y squared minus 2x. So I've got that here. So let me just grab it, make sure I have the same thing too. Yep, checks out. So what we're saying is y prime is 2y minus x squared over y squared minus 2x. And kind of a chain link here. I'm forcing it to equal 0. Okay. So I'm going to copy that down again, just down below here so we can really look at it. So really what we're saying is that 0 equals 2y minus x squared over y squared minus 2x, right? What we're saying is we want to find a point xy that makes the derivative 0. That makes y prime equal to 0. So there are no derivatives here, but we do need to rearrange and solve for x and y. It's hard, right? Because we've got both x's and y's in here, but there are a couple of things that we need to keep in mind, right? First off, we need to make sure that we don't divide by 0, right? So here, we can't have y squared minus 2x equals 0. In fact, there's no way that anything in the denominator can make this overall thing go to 0, right? Because I can't divide by 0. And so that would be my only shot. So that's something to keep in mind, right? The only way to make this whole thing 0 is if I make the numerator 0. Right? So here, I'll say makes y prime equal to 0 if 2y minus x squared equals 0. And that's going to be my only way to get the whole overall thing to be 0. Here, I'll say the denominator can't make a fraction 0. The denominator, drawing a blank. Denominator or denominator?
Domino. Now you've got me confused. We might as well move
yeah,
on.
I'm struggling with this I. I'm pretty sure it's I write denominator every day, so this is like a complete brain fart. Anyways, I'm sticking to it. The denominator, okay, can never make a fraction 0. All right, so that's something to keep in mind. So our only hope of setting this thing equal to 0 is finding an xy combination that makes 2y minus x squared equal to 0. So that boils things down quite a bit, right? So we need 2y minus x squared equal to 0. Can do. Probably the easiest thing is to move the the negative x squared to the right-hand side. So I get 2y equals x squared, and then y is x squared over 2. And then what? Yeah, then what? Here's the tricky part, okay? We need to bring this back to the original function, right? Because saying, oh, y can just be anything that is equal to x squared over 2, but we need to specify that it has to be on, so the point has to be on the Folium of Descartes, otherwise it won't work, right? And so this point needs to be on, so this point needs to be on, what's the original function? X to the 3 plus y to the 3 equals 6xy, right? Our original function. So what can I do? I can substitute y into here, and then all of a sudden I only have x's, which means if I only have one variable, I'll be able to solve for that and actually get a number, which is great. And then once I have a number for x, I can easily go back and solve for y. Right? But that's the hard part, is thinking, okay, what do I need to do here? So we can substitute y equals x squared over 2 into x to the 3 plus y to the 3 equals 6xy to solve for x. Oops, it said x but wrote y. Okay, there we go. So I have x to the 3 plus x squared over 2 to the power of 3. Right, just substituting y with x squared over 2 equals 6x times x squared over 2. Kind of now we're just working with exponents basically the whole way through. So I have x to the 3 plus x to the 2 times 3, right? When I bring that 3 inside, I have to bring it on both the x squared and the 2. So I get x to the 6 over 2 to the power of 3 is 8, which is going to be 6 over 2 is 3, and then x times x squared is x to the 3. Okay. You can go a couple of routes here. To me, it's tempting to find a common denominator, but I also see that I'll be able to simplify a little bit if I move this x to the 3 over to the right-hand side. Then I won't need a common denominator. So I have x to the 6 over 8 is 3x to the 3 minus x to the 3, right? That's 1x to the 3. So x to the 6, I'll keep it over 8 for another step, is 2x to the 3. Then I can multiply this 8 over, so I get x to the 6 equals 16x to the 3. Now I'm trying to solve for x, right? So eventually I'm moving towards x, and there might be other ways, kind of quicker ways that work for you to find it. I don't see any, but I don't know. Depends on how you rearrange things. But for me, what I'm seeing is this would be the quickest route, because now I can divide both sides by x to the 3, right? And because I have the same base, I can simplify. So x to the 6 over x to the 3 equals 16. X to the 6 minus 3 is x to the 3, which is 16. Oh. As long as we don't find x equals 0, right? So x to the 3 is can't be 0 because I'm dividing by it here, right? So here I'll just make a note. X to the 3 can't be equal to 0. Or maybe I should say as long as. But the only way that we would find that is if x equals 0, which it doesn't, so we're safe. So then solving for x is going to be the third root of 16. You can write 16 to the 1 over 3 if you want, but I'm just going to keep it as, or maybe I'll write it here. Or 16 to the power of 1 over 3. It depends on what's easier for you. Okay. 16, so the third root of 16, I'm just going to do it on my calculator here. 16 to the power of 1 divided by 3, I get x is roughly 2.519841, just to get an idea of where this thing is, right? And so we said, wow. We said out here, wow. Out here at the very edge, probably was at 3.3. And so this, it makes sense that it would be around 2.5-ish, right? It just looking at it. So far, so good. So now all we need to do is find the y value that makes that happen, right? And so here, just kind of plugging it in, what we found is that this is at the third root of 16. That's what we found. It took a lot of work, but we got there. So now what's nice is we already know, whoop, I scrolled past it. We already know that y equals x squared over 2, right? So now we don't need to do any more work here. Really. So then recall y equals x squared over 2. So then y is the third root of 16 to the power of 2 over 2. And lots of different ways that you could write that. But I would probably just leave it like that. That's the exact form. And usually WebAssign definitely wants the exact form most often. So then I'm going to do a little conclusion here on the same page. Therefore, the tangent line is horizontal. At the third root of 16 and the third root of 16, oops, cramming it in here. The third root of 16 squared. If you want to do 16 to the power of 2 over 3, that's fine. And then divide it by 2. That's a big question. Uh-oh. Looks like it took me past our usual break time. I'll ask my usual question then. Do you want to break now or do you want to end a little bit early?
I can keep powering on.
Say that again.
I can keep powering on.
We can do it. Also, ending early is always kind of nice. Yeah. I know we kind of went over, but can you imagine leaving this this problem halfway through? No way. Oh, we'd have to redo it all. All right, let's do it. Implicit differentiation. We're going to conquer it. Okay. So how do we conquer it? When do we want it? Wow, more examples. So let's do another example. I think I have, let me just go back here. Okay. I want to do this trig function because we haven't really dealt with trig functions. to be quite honest, I try to avoid trig functions. I don't think that they're that great. I know that's bad, but because I personally don't like trig functions. But that's bad, right? I shouldn't do that. So here I'm forcing us to do a trig function. So here we go. One thing, so what's nice is if you kind of take a step back and break down, just so you kind of remind yourself what rules you have to use, right? So here, the sine of x plus y, there's a y inside, right? But there's also a chain rule because you have x plus y inside the sine function. So there's a chain rule here. In fact, there's a chain rule inside a chain rule, right? Because y also has a chain rule. And then on the right-hand side, there's no chain rule for the cos of x. There is a chain rule for the y, just kind of implicitly. But also overall, we've got a y squared times cos x. We've got a product rule again. So there's a lot going on, right? Again, just to indicate that, hey, what I'm about to start doing is finding the derivative, not just manipulating this function. I will start with d dx, but just wrapped around this whole thing, sine of x plus y, I guess on both sides, is d dx of y squared cos x. Because once I've said that, then after that, it's assumed that I'm actually finding the derivative. Okie dokie. Remember the co-functions make negative. So that means the sine, the derivative of sine is just cosine, right? Because they're opposites. So I get the derivative of the outside is the cos of x plus y. But then I have to take the derivative of the inside. All right. I'm going to bump that over a bit. Times the derivative of the inside, which is going to be I have an extra step in the notes that I did here, but I think we can just go for it. Right, the derivative of the inside with respect to x is just going to be 1 plus y prime. Maybe that'll make it a little bit nicer to look at later too. So now, again, I've got basically...
Sorry, I don't quite understand how we got to cos x plus y 1 plus y prime. Where'd the one come from?
How about I don't skip the step that I just skipped? Might help. Forget this ever happened. Okay, so here the sine is my outside function and the x plus y is my inside function. So taking the derivative of the outside becomes the cosine, and then I evaluate it at the inside. So that's where I get the cos of x plus y. Right, that's the outside evaluated at the inside, but then I need to times it by, and I will show d dx of x plus y. And that's where that 1 plus y prime came from.
Okay, that makes more sense.
I'll do that in the next step. So then here, if I treat my first function as the y squared, remembering that itself is going to need a chain rule, right? And so that's where it gets a little bit dicey. And then here, I'll let this be g. So then I'll just jot down that I'm going to need f prime g plus f g prime, just as a quick reminder to myself mostly. So then I have the derivative of f is 2y times y prime. And I know how nasty d dx is here and y prime's here. Ugh. But then I have plus f, which is just y squared, times g prime, which is just a plain old function with respect to x. And so then I can take the derivative of cos x, which is negative sine x, times negative sine x. Oh, and I forgot a thing, didn't I? I did the derivative of f, but I need to multiply by g, which just is held at cos x. Sorry about that. So now the only thing I need to find the derivative of is the d dx of x plus y. So I'm going to write out everything else just as it is at cos of x plus y times 1 plus y prime, right? Because the y is just y to the power of 1. Just becomes 1 times y to the power of 0, but that's going to be 1. So 1 times y prime. So that's why we just go straight to y prime. And then I have 2y, y prime, cos x, minus y squared sine x, moving that negative out. Okay. What's the best way of dealing with this thing? I'd probably expand the cos xy inside, right? Because I'm now trying to solve for y prime, right? So let's just highlight where they are. Y prime. Solve for y prime. But to shake out the y prime from inside these brackets here, I think the easiest thing is just to expand the cos x plus y inside. So what I get is I get cos x plus y times 1, that's fine, plus y prime cos x plus y. And I'll keep it on the right-hand side for a little bit longer, equals 2y, y prime cos x minus y squared sine x. So now I'm trying to collect all my y primes. So I bump the cos x plus y to the right-hand side. I get y prime cos x plus y minus 2y, y prime cos x equals negative y squared sine x minus cos of x plus y. Even though this looks really nasty, the math that we're doing here is not that extreme, right? It's kind of expanding, collecting like terms, but it can be really easy to kind of muck it up along the way. So now I'm going to factor out a common y prime. So y prime times the cosine of x plus y minus 2y cos x equals negative y squared. Let me see if, yeah, negative y squared sine x minus cos of x plus y. So close. All I need to do now, right, is divide both sides by all that cos x plus y minus 2y cos x. So here we go. Y prime is negative y squared sine x minus the cos of x plus y divided by the cos of x plus y minus 2y cos x. And I actually don't see anything that I could simplify with here, so I'm just going to leave it. But I will put a smiley face because that was hard, right? It was long. Okay. How about another example? A little bit easier this, well, okay, I shouldn't say that. So
Let's just get it over with.
there's another thing, but wait, there's more. Let's do it. So now we're finding the second derivative. So almost exactly like, I'll put it on its own page here. Almost exactly like when we found the first derivative, we had to rearrange and solve for y prime. So when we're finding the second derivative is going to also involve y primes. And so what we're going to do is we're going to have y prime from the first derivative, and then we substitute it into the second derivative. And that's how we're going to find the second derivative. So it's a little bit more work, but here we go. So we want to find the second derivative of this thing. So I have, I want to find the first derivative first. D dx x to the fourth plus y to the fourth equals d dx of 16. Back to kind of where we started earlier, right? So not bad. I get 4x to the 3 plus 4y to the 3 times y prime equals 0. Right, making sure you take the derivative of y as if it's just the outside, but then make sure you multiply by y prime. So then y prime, solving for y prime is not that bad. I get 4y to the 3y prime is negative 4x to the 3. So then y prime is negative 4x to the 3 over 4y to the 3. Yes, everything will be with respect to x. Right. Yeah, let me just flip through, especially for the quiz. Yeah, it's all with respect to x. Okay. So now I have y prime. Hey, that was not bad. Now that we've done some hard ones, right? But now I want to find the second derivative, right? And so the second derivative means that what I'm trying to do is I'm trying to take d dx of I guess I can cancel the 4s. Let's do that. Clean it up a little bit. 4 over 4. But I already wrote, so negative x to the 3 over y to the 3. That's better. So I want to take the derivative of negative x to the 3 over y to the 3. Right? That would be my second derivative. Here, we need to notice that we have the quotient rule. You remember the quotient rule? The quotient rule is f prime g minus f g prime over g squared. In this case, our f, let's let f be, let's let f be negative x to the 3, just so we don't have to deal with that negative. So let f be negative x to the 3, and then I'm going to let g be y to the 3. Doesn't matter which one you make the negative, but just make sure only one of them is the negative. So, okay, now we can do our quotient rule. It's been a while, but okay, so f prime, that's fair enough. Negative 3x squared times g, which is y to the 3, minus, remember to subtract, unlike the product rule, minus negative x to the 3 times 3y squared y prime. Kind of ran out of room there. In fact, I'm going to squeeze it over just because that's an important part. So 3y squared times y prime, right? When we take the derivative with respect to x. But then it's over g squared, which is y to the 3 squared. So here, the key is to say that, okay, well, this is equal to y prime. So this is equal to y prime. So what can I do? I can substitute that in here. And that's the only time that I don't have just an x or a y in this function, right? So once I substitute that in, then I'll have the second derivative, right? But I don't want to have a derivative with a derivative inside. That doesn't look right. So so that's the key to finding the second derivative with implicit differentiation is you plug in the old derivative. Now it's, I want to say, just a matter of simplification. It's going to be a little bit involved, right? But we can do it. Substitute y prime equals negative x to the 3 over y to the 3 into, and I'll call this y double prime. So I have negative 3x squared times y to the 3. I'm just moving it over to give myself some more room here. Y to the 3 minus, maybe I'll just change it to plus, minus negative. So plus x to the 3 times 3y squared times negative x to the 3 over y to the 3, right? Substituting that in. And then it's over y to the 6. There are a couple of things that you could do, right? Especially because, well, first thing I'm going to do is I'm going to bump this negative outside, and then I'm going to be able to cancel my y squared in the numerator, leaving 1 in the denominator, 1y. And then x to the 3 times x to the 3, I can simplify that a little bit. So to start off with, I'm going to do negative 3x squared y to the 3 minus x to the 6, and I'll bump that 3 outside. 3x to the 6th over y. To simplify that. But then it's over y to the 6th. There are a few routes you can take here. I am going to force a common denominator in the numerator. I know, messy. But then I'll have a fraction over a fraction, which I can then flip and multiply, right, to simplify. So I'm going to force a common denominator here times y over y, which means that puts me at negative 3x squared y to the fourth minus 3x squared over y to the sixth. And then I just want to remind myself that y to the sixth are 1, right? Because now I can flip that denominator and then multiply across, which puts me at negative 3x squared y to the fourth minus 3x squared
Hold up.
over y.
I lost something here. The x to the 3. Yeah, how did you get x squared in that second bit?
Maybe I didn't. Should be x
Because I was
to
pretty
the,
sure it was x to the 6.
yeah. And it is.
Good to know. I was getting very worried.
Yeah, I'm just seeing if you guys are no, I'm
Gotta keep us on our
sorry.
toes, apparently.
Hey, you guys are so good. Look at me being sloppy. The idea was there, but okay, good. Let me go back, pretend that didn't happen. X to the 3 times x to the 3 is x to the 6. There. Just pretend it didn't happen. It did happen. Maybe I should check my notes every now and then. Negative 3x squared y. Okay, we are good. Hopefully. Good. So I can multiply across here, and I'm so close to keeping it on one page. Oh. How do I keep it on? Just need one more line. Right, because now I just need to multiply across, so I get y to the 7, and I'm feeling pretty good about that. In the denominator, there's nothing really, so you could start to simplify even more, right, by pulling out a negative 3, so a common negative 3x squared, but I don't really see the point. We're done here, right? As soon as we've got it as a fraction, I would call it quits. And I know that's really hard to know when can you stop. There's no hard and fast rule, unfortunately. But I would say as soon as it's all kind of one clean fraction, you can call it quits.
Forgiving definition of clean.
Yeah. You won't be able to cancel the y. You want to be careful, right? Because there's no y over here, right? Because in order to cancel that y, you would need to be able to pull it out from both sides. So yeah, you just want to be careful. All right, cool. Let's do, it's a big section, but we're just going to do the derivatives of inverse trig functions. You guys don't have to memorize them or anything. You can just, but make sure that you have them available, just like the other derivatives that we've established, right? And so let's talk about derivatives of inverse trig functions. And I've given them to you there in the handout. Copy. And they look really weird. Oh. Yeah, it should be So y to the, did I do that right? Oh yeah, it's because I multiplied by a y to get that common denominator. So it was y to the 3, and then I multiplied to get that one. To get all over y. Okay, yeah, so these derivatives are weird, okay? I want to go through one of the proofs. I think we're doing the inverse sine. All the proofs follow the same structure after this, so if you wanted to work through the proofs, that's great. You don't have to. But we're going to look at the proof for the inverse sine of x. So we will prove that, that d dx of sine inverse of x equals 1 over the root of 1 minus x squared. Yeah. So we'll prove that one. And then I'll do a little follow up here. The methods for proving the others follow the same structure. The method for proving the others, and it's a good exercise in just implicit differentiation, so that part's kind of fun. The method for proving the others follow the same structure. What's nice about proofs is, well, you know what you're working towards, right? You're trying to show that this is true, but easier said than done, right? Okay, so what we want to talk about first is what does it mean? So sine inverse or arc sine, let's say sine inverse of x is the same as arc sine of x. And usually if you're typing, of course, arc sine is a lot quicker and easier to type. So that's why we sometimes use arc sine, but it's sine inverse or arc sine, they're equivalent. And so what we want to recall is what it means to be the inverse. Well, if the sine inverse of x equals y, that's the same as saying, so remember, probably from high school, I would say, if you're working with sine inverse, right, then you can move it over to the other side and it just becomes sine y. So then this is the same as saying x equals the sine of y, right? No inverse anymore because it's shifted over. And I'm going to skip talking about the domain because it's adding more work that I don't really care about. But I will write it down here. The domain is from negative pi over 2. So this is for your y's, and y is going to positive pi over 2. But we're not focusing on, but we won't focus on the domain. But that said, I will kind of make some comments along the way here in case you're working through your own example. But the meat and potatoes here is x equals sine y. So now I have this implicit function, right? I can't solve for y because then I get back to the inverse sine of x. That doesn't help me. That's what I'm trying to prove. So here I have x equals the sine of y, and this is an implicit function. Oops. So I can differentiate this thing, right? In fact, maybe I'll swing it around so that the sine y is on the left. Because pretty quick, the derivative of x with respect to x is just going to go to 1, right? So it might be nicer to have sine y equals x. And now I'm going to take the derivative. Decided to just throw it on there. That's okay. So if I'm taking the derivative of sine y, which is an implicit function, right? And so I can take the derivative of the outside, which is sine, so that makes a derivative of cos y. Right? Derivative of sine is cosine, and then evaluated at the inside is just y. But then I also have times y prime times the derivative of the inside, which is y. And then the derivative of x is 1. Okay. So here, solving for y prime again, I get y prime is 1 over the cos of y. Here, I'm going to make a note. This is where we need to make sure that cos y isn't equal to 0. So it actually adjusts our domain to not be inclusive of the endpoints anymore. Okay. But like I said, we're not going to focus on it, but I will make a side note here. We need to adjust the domain so cos y does not equal 0. So our new domain is that y is not including negative pi over 2 up to pi over 2. That's just a side note. It actually gets a little bit pickly, so that's why I'm skipping it. You have to kind of map it out and look, where does it equal 0? Well, it equals 0 on the cosine equals 0 on the y-axis. Anyways, so just ignore it for now. We can go back to it, but I probably won't. It's negative. So now the key to these identities is to remember that cos squared whatever plus sine squared of whatever we're talking about equals 1. And so that's how we're going to get out of this jam of having cos y. So recall, and this is the big thing, is using this identity, that the cos squared y plus sine squared y equals 1, which means that cos y, or cos squared y, let's start there. So cos squared y equals 1 minus sine squared y. But remember, the squares, you can just pull them outside. So cos squared y is cos y times cos y. So you get cos y equals the square root of 1 minus sine squared y. How does that help us? Well, we just established, or kind of what we did in the beginning, right, was that sine y equals x. So now if I have sine squared y, that's the same as x squared, right? So, okay. And that's the tricky part. And from earlier, x equals sine y. Therefore, x squared equals sine squared y. So now I can cobble this all together, and I know I've extended our, oh, come on, 1 over cos y, which we're going to replace. So here, I'll just write it out again. 1 over cos y becomes 1 over the root of 1 minus sine squared y, which becomes 1 over the root of 1 minus x squared. And that's the end of that. Did it. And I'm sorry.
No problem.
You guys just stop believing me when I say end early.
Quite frankly, just looking at this is making me go like, yeah, the extra time covering this is definitely necessary because, yeah. And
it's hard. It's hard.
If you remember from Friday, I asked that we have like a little bit of a longer review session on this specifically because the second I see signs, whether or not they have superscripts, my mind just starts shutting down in terror.
I know, it's like trig functions, no way, no thank you. You got it. Yeah, we have two kind of bigger examples left on the handout, so we'll do those for sure, both of which have trig functions, so that's a good thing, I guess. And I think they're kind of, the second one is like a chain rule inside a product rule, pretty sure. Kind of a big
From what I'm seeing from the handout, yeah.
Yeah. So we'll definitely come back and work on this some more. But yeah.
All right. I'm going to run away now. See you Friday.
All right. See you Friday.